All right, let's start today with kind of a rehashing of something that we saw in Gen Chem 1, and that is the conjugate acid-base pair. Um, and what we want to talk about is we want to be able to identify these pairs when they exist so that we have a better idea of kind of how to treat the individual ions when they start appearing in chemical reactions. And so what we covered in 105 was we covered the idea of Bronsted theory. And in Bronsted theory, we saw that, okay, this was my acid, and this water is my base. And if we flipped it over to the other side, we could see that there was a related pair that if we flipped the reaction around, would behave in the opposite kind of manner. So the bromide ion, having lost that hydrogen, is a conjugate base to the hydrobromic acid, meaning that it could, if prompted, act as a base in a normal situation and reproduce the hydrogen bromide hydrobromic acid again after undergoing that base reaction. And the hydronium, same thing. The hydronium is a conjugate acid to the water, where if we find hydronium acting as an acid, it's going to reform the water. And what we get out of these are pairings, conjugate acid-base pairs, where I can point to a pair of reactants in an acid-base reaction and say, these two species are related to each other in some kind of way. Well, the same is true for weak acids and weak bases, where I can look at the reaction and see, okay, the hydrogen from HF is going to the water. So HF is an acid and water is a base. But now that I have a reversibility to this, I can look on the other side of the reaction and say, well, hold on a second. The hydronium gives up a hydrogen to the fluoride in the reverse reaction. So that means that the hydronium is acting as an acid and the fluoride is acting as a base. And what we'll see in those scenarios again is that we have a set of pairs. I have an acid on each side and a base on each side. And I can pair together the acid of one side to the base on the other side and find a conjugate pair between them. And I can pair together the base on the one side with the acid on the other and find a conjugate pair between them. So we very lightly covered this in 105. We spent more time talking about identifying the acid in the base. We didn't talk so much about the conjugate part of it, unless we saw that there's a little bit of confusion because I know in my sections, I would have students that would try to write acid and base for the products instead of the reactants. And generally speaking, they would be correct if the reactions were reversible, but we weren't showing reversible reactions back then. Now, here's the thing to understand. If a conjugate species like bromide or like fluoride were to react with water or with something else as an acid or a base, well, if they can do it in this acid-base reaction that we have here, what's to say that they couldn't do that with water and act as an acid or a base themselves? So take bromide out of this particular reaction and let's just put it into water. Will bromide ion react with water as a base? And the answer is it could. But the extent to which it does, we would have to monitor. We would have to calculate. And we would have to know some kind of an equilibrium constant for that to get a full idea of just how much that reaction takes place. And we would make the same kind of argument with the fluoride ion. Fluoride ion could react with water to create hydrogen fluoride and hydroxide. It could act as a base. To what extent does that actually occur? And if I'm going to compare the bromine and the fluoride to each other, how do I know which one would act stronger as a base compared to the other? So just in review, we should be able to, through the use of this reversibility, through the use of our definitions of the Bronsted-Lowry acid-base theory, or even Lewis theory, we should be able to identify acids and bases on reactions and identify conjugate pairs based upon their collective adding or subtracting of a hydrogen. So before we get too deep with the other stuff here, let's just take a moment and do a little bit of practice with identifying acids and bases and their conjugates. So here I have the bisulfite ion, HSO3 -1, reacting with water to make the sulfite ion and hydronium. All right, so let's start with the easy part of this. Between the bisulfite and the water, which one is acting as an acid? Where's the hydrogen going? Yeah. Sulfite's the acid, bisulfite's the acid because we've got the hydrogen going from there to the water, and we can see the result of that because the bisulfite is now one less hydrogen and the water was one extra hydrogen. So under that definition, the bisulfite is acid, the water is base, and then the conjugates would be on the product side. So we've got a conjugate and a conjugate here. What are the conjugates? How do I identify them? Well, two things. One, I could look at, okay, clearly these two are a pair. They're only different by one hydrogen. And so if this one we identified as acid, the other one must be base. And so I could make that determination that way. And I could make a similar kind of determination for the water pair. Water and hydronium, they're one hydrogen apart. This one acted as a base, so this one must be its conjugate acid because you can't have a conjugate base to another base. They're not conjugate base pairs, they're conjugate acid base pairs. So every conjugate pair has to have an acid and it has to have a base. Now, the other approach that we could look at is we could reverse the reaction and see how it's behaving. And what we would see is that in the reverse reaction, the hydronium is giving up a hydrogen to the sulfur here, or more specifically to the sulfite. And so in that scenario, the hydronium ion is acting as an acid because it's giving up a hydrogen, and the sulfite is acting as a base because it's accepting that hydrogen. All right, in our second example, again, pretty easy to identify pairs. The bisulfate, hydrogen sulfate ion, and the sulfate ion are an obvious pair. And the carbonate and hydrogen carbonate are another obvious pair. Again, it's easy to pick up on pairs because they're one hydrogen apart from each other. But if I'm identifying what they're doing, again, I need to look at, well, what is happening? Hydrogen is going from the hydrogen sulfate to the carbonate. So that is acid behavior. Carbonate adding that hydrogen is base behavior. On the flip side, I can see that the hydrogen in hydrogen carbonate is donating its hydrogen to the sulfate. So that is acid behavior, but it is conjugate acid behavior because it's on the product side. And that means that the sulfate is a conjugate base. And again, if I look at each pair individually, in the orange grouping, I've got an acid and a conjugate base. That makes sense. I should have one of each. In the yellow pairing, I've got a base and a conjugate acid. Again, should make sense. They need to be paired. All right, any questions with this? Now, to go about answering the question here, which one is stronger, which one is weaker? Well, the answer to that question relies on the kind of complementary nature of acid-base pairs. Acid-base pairs are inversely related in terms of their strength. The stronger the acid is, the weaker the base is going to be, and vice versa. So when I look at acids that are on the stronger side of the scale, what I'm going to find is that those conjugates are on the weaker side of things. So piggybacking off of what we talked about yesterday, here's hydrochloric acid on the scale. We would anticipate that hydrobromic acid, because that bromine atom is larger, we would anticipate that hydrobromic acid is actually stronger than hydrochloric, which means that the bromide ion is an even weaker acid, or excuse me, an even weaker base than the chloride would be. So which is a better base, the fluoride ion or the bromide ion? It would be the fluoride ion. The weaker the acid, the better its conjugate base is going to be at being a base. And quantitatively, we can relate these two to each other with this equation. If I take a conjugate pair and I multiply the conjugate pair's K values, so the Ka for the acid and the Kb for its conjugate base, if I multiply those two together, I will get Kw. Remember, Kw is 1 times 10 to the negative 14th. So if my Ka value is 6 million, like is the case for something like nitric acid, then my Kb value is going to be incredibly small, to the point where we almost consider it to be not worth pursuit. In fact, if a conjugate value falls below Kw, we actually don't even consider it to be acidic or basic at all. So if Ka falls below 1 times 10 to the negative 14th, then we consider it to be non-acidic, because water actually produces more hydronium than it does. And if Kb falls below 1.10 to the negative 14th, we consider that ion to be non-basic, because again, water creates more hydroxide than it would. So on the high end of the scale here, where we've got our super strong acids, those conjugate bases actually have no impact on the pH of water. We would consider them neutral ions. So with these in mind, then, let's list out these ions in order of decreasing strength as far as base behavior goes. And so we're looking for fluoride, chloride, hydroxide, acetate, and hydride. And so right away, we can see hydride is on the strongest end here. Hydrogen molecule, elemental hydrogen, is practically non-acidic. So its conjugate base, the hydride ion, would be extremely basic. So hydride would be the strongest base. And then let's go from here. From hydride, we would go to hydroxide. So the hydroxide ions are relatively strong base, by comparison at least. Going from there, we find the acetate ion. So CH3COO minus. And then from there, we see the fluoride ion. And then finally, the chloride ion, which, since its conjugate acid, hydrochloric acid, is actually a strong acid, its base behavior is practically nothing. So the ultimate application of this particular concept is in the production of salt solutions. And the reason we want to focus on salt solutions here is because, for the most part, salt solutions, up until this point, we've never really considered the acid-base characteristics of those. We haven't had a whole lot of reason to. It's not like we're walking up to a solution of sodium nitrate and saying, I wonder what the pH of that is. Really hasn't crossed our mind, or hasn't really needed to. But now that we're starting to look at things a little bit more closely, and we're starting to monitor pH of a lot of different systems, and especially as we start to look into some of that qualitative analysis stuff. Yesterday in lab, we started the group 2 analysis, the acid insoluble sulfides. Well, one of the reasons we had to do the reaction the way that we did with the thioacetamide, as opposed to just say sodium sulfide or ammonium sulfide to give us the sulfur, is because, well, sulfides are basic in solution. And so if we just drop in sodium sulfide into our reaction mixture, we're not going to get what we want, because we need the pH to be below 7 to pull out these ones that are only insoluble in acid, not the ones that are insoluble in base. And if we reverse the order, it actually creates more complicating factors when we have more than just those ions that we're looking for in this analysis. If I have a large mixture of ions that are from varying groups, I need to pull them out in the correct order so that there isn't any cross-contamination. So to answer the question about salt and pH, what we really have to think about are the conjugates themselves. What do the conjugates do? What do the conjugates look like? And the questions that we have to answer are things like these. How does that ion react with water? What is it a conjugate of? Is it a conjugate of something strong or something weak? Will it react with water to form a hydroxide or to form a hydronium ion? If the answer to all those questions is no, then we're probably dealing with some sort of a neutral salt that the pH is going to remain around 7. But if the answer to any of those questions is yes, then we need to know, well, how does it do it, and what should we expect? And then furthermore, at the end of class, we'll actually get into calculations for, well, what is the pH actually going to be, or at least what should we expect it to be based off of some equilibrium calculations. So let's start by talking about anions. Anions can break down into two categories. Anions can either be inert, meaning that they do not react with water at all, or they'll be basic. What are some common examples of inert anions? Well, these would be the conjugate bases of our strong acids. So we just put up a list of strong acids here on the board. Any of the anions attached to those strong acids are going to be inert toward water. So that means chlorides, bromides, nitrates. We have to be careful with sulfuric acid. Sulfuric acid is not going to fit perfectly into that mode, because its first deprotonation is going to give us the hydrogen sulfate ion, and the hydrogen sulfate ion is not inert toward water. It has a Ka value that we would have to consider. But aside from that, everything else here that is monoprotic, all of those anions are inert toward water. The ions that are basic are the conjugate bases of weak acids. So these are things like oxalate, sulfide, hydrogen sulfite, acetate, fluoride, carbonate. So think of all of your kind of classic weak acid combinations. Their conjugate ions, their conjugate bases are usually going to be basic. And the weaker the acid is, the stronger that base solution is going to be. So that's the anion side. On the cation side, again, two different kinds of modes of thinking. For the first mode, the inert cations. These would be the conjugate acids of the strong bases. And what we really want to talk about here are the metal ions. So the sodium ion, the lithium ion, the calcium ion. So basically the ions that are on these lists here that we talked about as being strong bases, your group 1 and your group 2s, those are going to, generally speaking, be inert. Ions that are acidic are going to be metal ions or ammonium ion that can react with water. So probably the best and most well-known example is that of ammonium. So with ammonium, we can see hydrogen donated to the water to make hydronium and ammonia as its conjugate base. For the metal ions that are acidic, it's a little bit more complicated than that. It has to do with formation of complexes and the reaction of some of those complexes to create hydronium. We'll stay clear of most of the nitty-gritty for those, just with an understanding that things like iron 2 plus or aluminum or copper 2 ion, these will have a slightly acidic kind of tendency to them. The wild cards in these evaluations are the amphiprotic ions. Now, if you remember from our definition on Friday, amphiprotic means that it can act as an acid or as a base. So common examples of these are the in-between ions of polyprotic acids. So we're looking at the bisulfites, the bisulfates, the bicarbonates, the dihydrogen phosphates, the monohydrogen phosphate ions. Those ones are amphiprotic. The way to determine whether they act acidically or basically is we have to compare their Ka and their Kb values to each other. And so most of these have a reported Ka value. To find the Kb value for them, you take that Ka and you divide it into Kw. A general rule of thumb that we can use because of this equation, if the Ka for the ion is greater than 1 times 10 to the negative 7th, we can assume that it's going to be acidic. If Ka is less than that, then we know it's going to be basic. And that's just a simple application of understanding this bottom equation here. Now, if we have to actually calculate it, we'll have to use the equation. But generally speaking, we can use a rule of thumb there. And the rule of thumb generally works out okay for us because, if we come back to So here's carbonic acid, for example. Carbonic acid on its own is not terribly acidic to start with, 4.4 times 10 to the negative seventh. For the bicarbonate ion, its Ka is 4.7 times 10 to the negative 11th. That's well below the threshold of 10 to the negative seventh. And so we would predict that the bicarbonate ion would actually act basically in solution. And in fact, it does. Bicarbonate is a very common antacid because of its weakly basic behavior. It's going to go that direction. The second deprotonation of arsenic acid, on the other hand, we can see that the first one's definitely acidic. The second one is also acidic. The third one, so this would be H3ASO4, H2ASO4 negative 1 would be acidic. HASO4 negative 2 would be basic under those guidelines. For citric acid, under those guidelines, all three of the forms are acidic. And so we can use that as, again, just kind of a guideline here to kind of put us in the right direction. And on the base side, what we'll see is that, yes, these bases here that have the high values are they're more basic than water, but that second loss of hydroxide is going to be pretty hard to come by for some of those hydroxides there. All right, let's take a break here. We've been going for over an hour.